Okay, everybody. Today we're going to continue our discussion about plate tectonics by talking about seafloor spreading. Today you should be able to explain seafloor spreading and then assess the evidence that supports seafloor spreading. So first, some background. When they first started mapping the ocean floor, they did it using a rope that they would lower with a weight on the end that they would lower to the seafloor, and using that they could determine the depth of the ocean. This was how they measured water depth for centuries. There was a mark on these ropes about every fathom, which is about every 6 feet or so. So this was how they measured the ocean floor, mapped the ocean floor until World War I, which is when the use of sound waves was introduced by German scientists to detect submarines. Today's technology for sonar and fish finders works a lot of the same way. It's kind of like how bats use echolocation. So how does that work? Basically, sound waves are emitted from the bottom of a ship, and they bounce off the ocean floor, or submarine, or fish, or whatever you're measuring, and return to the boat. The longer those waves take to return to the boat, the deeper the object or the ocean floor is. So this data, when they were first mapping the ocean floor, this data was collected and sent back to scientists and cartographers on land so that they could chart and map what the bottom of the ocean floor looked like. At the time, it was assumed that the ocean floor was relatively flat and featureless. However, using the data collected, researchers discovered that an underwater system of ridges, mountains, and valleys existed like those that we know of on the continents. So the first map of the ocean floor using this data was created by an American cartographer named Marie Tharp. Her data was presented in 1957, but it wasn't published until 1977. She was convinced that Wegener's theory, the one about continental drift, remember, was correct, and that the ridges were showing up on the data, and the ridges that were showing up on the data were proof of this. Most scientists at the time did not believe her, as is common when scientists first make discoveries. So another scientist at the time was mapping earthquakes on the ocean floor, and his map matched hers. The earthquakes he was mapping were common near the ridges that she was mapping, which was an interesting correlation. So, what is a mid-ocean ridge? So in the Atlantic, the Pacific, and other oceans around the world, there is a system of ridges that we call mid-ocean ridges. These are the things that were showing up on Mrs. Tharp's maps. These are what the data was showing. There's only one place on Earth where there's a mid-ocean ridge that is actually above water, and that's in Iceland, in a place called Thingvellir National Park. This is where the North American plate and the Eurasian plate are pulling apart. And in the picture here, the little path down the middle, that is actually between the two continental plates. Those plates are separating at about 1 inch per year. So slowly that rift there is coming apart. That's why Iceland is so volcanic. You'll hear them on the news a lot about volcanoes. So the seafloor moves. Okay, but why? So in the 60s, a Princeton University scientist named Harry Hess suggested an explanation or hypothesis. His now famous theory is known as seafloor spreading. He proposed that the hot, less dense material, magma, below Earth's crust rises toward the surface at the mid-ocean ridges. At the surface, the magma cools and hardens into new rock. Over time, that rock slides sideways, carrying the seafloor away from the ridge in both directions, allowing fresh magma to bubble up between the plates and create new plate. So, as the seafloor spreads apart at the mid-ocean ridge, new seafloor is created. And the old seafloor moves away from the ridge in opposite directions. So, it's spreading, right? Okay, but can we prove it? Do we have evidence? So, in 1968, scientists above a research ship called the Glomar Challenger began gathering information about the rocks on the seafloor. It was a drilling and coring ship that worked between 68 and 83 in the Atlantic, Pacific, and Indian Oceans. Scientists on the ship found that the youngest rocks on the ocean floor are located at the mid-ocean ridges. And the ages of the rocks become increasingly older in samples obtained from further from the ridges, which is consistent with what we would expect for seafloor spreading. As molten material is forced upward along the ridges, it brings heat and chemicals to support exotic life forms in deep ocean water, these life forms are called extremophiles. You may have heard about those in biology class. So what other evidence do we have? We have magnetic clues as well. So we know from previous units that Earth has a imaginary bar magnet through the middle. And for all intents and purposes, north on the bar magnet faces geographic north and south faces south. However, that occasionally flips, and the magnetic north will face geographic south on occasion. These reversals are recorded in new rocks that are formed while it is reversed. So along the mid-ocean ridges, it'll tell you which way the magnetic field is facing. The newly formed iron minerals will record whatever direction magnetic north is facing. They'll all line up. So using a sensing device called a magnometer, to detect magnetic fields, scientists found that rocks on the ocean floor show periods of magnetic reversals. So it shows when the magnetic poles reverse. The magnetic alignment in the rocks reverses back and forth over time in strips that are parallel to the mid-ocean ridges. And a strong magnetic reading is recorded when the polarity of a rock is the same as the polarity of Earth's magnetic field today. So we can tell, and the other thing is they match on both sides of the ridge. So the time periods match because it's even. So this discovery proves strong support that the seafloor spreading was indeed occurring, and this helped explain how the crust could move apart, which was something that continental drift hypothesis on its own cannot really explain. We'll get more into that with tomorrow's lesson, but if you have any questions, think on this PowerPoint. If you have any questions, you can write them down and we can discuss them tomorrow in class. Otherwise, have a good evening.